Spoštovane kolegice in kolegi, cenjena publika, veliko veselje mi je, da vas lahko danes v tej dvorani pozdravim v imenu Slovenske akademije znanosti in umetnosti na dogodku, ki obeležuje 50-letnico delovanja seminarja za kompleksno analizo v Ljubljani. To je tudi edina stvar, ki jo bom povedal po slovensko. Okay, so now we switch to English. If you were afraid that we stay in Slovenia, no. But if I repeat again, it is my great pleasure to welcome my colleagues, the honored guests, especially my good friend Josip Globevnik, Pico to us, on this occasion of celebrating the 50th anniversary of the Seminar for Complex Analysis in Ljubljana. So this seminar was established in 1975 by Josip Globevnik, and he was also managing it by himself, more or less, for the first almost 4 decades. And I'm happy to say that the seed that he had sown at that time, 50 years ago, had taken very good roots, as is clear from today's audience. And we are also, I think, joined by some colleagues who are on Zoom or on YouTube. And the seminar developed really well after modest beginnings, of course. And now it's actually covering areas much wider than just complex analysis. Also complex geometry, complex dynamics, other parts of analysis like partial differential equations, and so forth, and some lot of geometry and so forth. So it's only for the sake of tradition that we do not change the name, that is still the Seminar for Complex Analysis. And I'm very happy that today we have with us 3 distinguished guests whom I thank that they accepted the invitation to come to Ljubljana on this occasion and give lectures. Before we continue, I now wish to ask the Dean of the Faculty of Mathematics and Physics. So the seminar is actually running under 2 institutions, Faculty of Mathematics and Physics of the University of Ljubljana and the Institute of Mathematics, Physics and Mechanics in Ljubljana. And so I kindly invite the Dean of the Faculty, Professor Emil Žagar, to say a few words.
Thank you very much, Franci. Dear members of the seminar, dear distinguished foreign speakers, dear guests, it is my pleasure to be here at the 50th anniversary of the Complex Analysis Seminar. The seminar is undoubtedly the most prestigious seminar at the Faculty of Mathematics and Physics, but I would say that this is also one of the most eminent seminars in the entire university. 2 members of the seminar, Professor Globevnik, the founder and the head of the seminar for several years, and his successor, Professor Forstneric, are members of the Slovenian Society of Sciences and Arts, and this is a really great achievement of the seminar. Also, other members of the seminar are eminent Slovenian mathematicians in the field of complex analysis and related fields. So this is really a nice occasion to be here. I'm pretty sure that this afternoon will be full of high-level mathematics, but also memories, because 50 years is a long period. And I wish you a great afternoon, and I'm looking forward for the next major anniversary. So thank you very much.
Thank you very much, Emil, for your kind words. And well, now it's my pleasure to invite Peter Schemerl, the director of the Institute for Mathematics, Physics and Mechanics.
Thank you. The role on behalf of the Institute of Mathematics, Physics and Mechanics, I would like to say that we are happy to be together with the faculty, the host of this seminar, No doubt this is the strongest, as Emil already said, the strongest research group in our country, featuring two leading mathematicians, academicians, Professor Glubevnik and Professor Forsnerich. And it's not surprising that around them, a very dynamical research group has formed, and I can see in this group future leaders of Slovenian Mathematical School. I would like to say that we are grateful to this seminar, first for you are most responsible for the high reputation of our institute, and second, this might be even more important because you have been for us an example that inspires all of the rest of us to be a little bit better than we would be without you, so thank you. So I'm happy to congratulate you for this anniversary, and I wish you a lot of success in the second half of the first century of your existence. Thank you.
Thank you so much, Peter. And well, now it's the time to begin, and the official scientific program. And our first speaker of this afternoon will be Professor Frank Kučebauch from the University of Bern. We have known with Frank for a long time now, almost 3 decades, when he first visited Ljubljana, and he has been our frequent visitor after that many times. So Frank is one of the leading researchers worldwide in the areas of complex geometry, which is now often called elliptic complex geometry, and also the theory of the density property and so forth. It has to do with complex manifolds which are highly symmetric. They have a lot of holomorphic symmetries. He contributed solutions of many outstanding open problems and had several publications in really top-level journals, including such as Annals of Mathematics and so on. And he has a really good research group, and many people came from this research group. Many young researchers, new PhDs, came from this research group in Bern. And okay, now today he will speak. Oh, we don't have the title here, but he will speak about holomorphic factorization of holomorphic matrices. I think I got it right. Please.
Thank you. Can we just open the file? Probably I have to maybe just try with push the file, right?
It's your name there.
So, okay. Can you help me make it faster? Okay, I'm sorry. I was here very often, but I didn't manage to deal with the computer. Sorry. Thanks a lot. So, it is a great honor for me to be present at such a nice anniversary, and I welcome you everyone to my talk, which will be speaking about a little piece of mathematics which has grown here in Slovenia in this seminar. Okay, so Professor Schemmel, I feel a little bit, okay. Yeah. I was not aware of talking in front of the specialist of linear algebra, but there are other people. Okay, so what is the problem? It's well known. You have a matrix of determinant 1, and you can write it as a product of elementary matrices, where elementary matrices are just those. Wait a minute, where's the pointer here? Sorry. Yeah. Oops, yeah. Those which have ones at the diagonal and one entry outside the diagonal, possibly non-zero. Of course, you can put all those which are lower triangular into 1, and all those which are upper triangular into 1. And then you ask about writing a matrix in SLNC as a product of upper and lower triangular unipotent matrices, which are called unitriangular matrices, right? So here is a shorthand notation. It means that all this triangle is filled. It has n times n minus 1 over 2 entries. And yeah, of course, the specialists know that 4 matrices is sufficient. So how do we prove that? It's essentially the Gauss elimination process, right? Because these elementary matrices, if we multiply it from the left, they are elementary row operations, multiply from the right, elementary column operations. And so what we have to do by elementary row or column operations, bring an arbitrary matrix into the identity matrix, right? So yeah, this adding multiples of a row to another, I already explained. Sometimes we interchange rows. This is not inside determinant 1. So what we do, we change 2 rows and change the sign of one of the row. And here you see how you make it by these elementary transformations. And it's not important that we change the sign. It's just important where do we put an entry in a certain column which is non-zero, right? So, and then when we end up with a diagonal matrix, we have this little thing which shows you that you can even make the diagonal to 1s, right? By inductively applying this. It has the name Whitehead lemma. So you can check this calculation. It's a very simple thing. And my talk will be about what if the matrix is not a fixed matrix, but depends on a certain parameter. Could be continuous depending, could be polynomial depending, or could be holomorphic. And the question would be whether these upper and lower triangular unipotent matrices can be chosen in the same way as our matrix depends on the parameter x, also depending on x. So now we are not having a fixed matrix. We are trying to find like maps from a space X, which is sort of a parameter space, into, yeah, I already told you this is the size of this triangle. Okay, so you can formulate this by using the language of rings. The rings we are talking about are rings of functions from if X is a topological space, we are talking about continuous function. We could talk about polynomial function if X is an algebraic variety, or if X is a complex space, we can talk about holomorphic functions. And the entries in our matrix, which depend on the parameter, can be just viewed as elements in this ring. And in the 1950s, something called K-theory of rings was created just because of these questions of factorization. And we are talking about special linear group over a ring. So the ring is now this parameter dependence, the functions. And we wonder whether this is a product of elementary matrices or unitriangular matrices exactly over that ring. So the entries are in the same ring, right? So in this language, take whatever nice ring with 1, commutative, associative, and the set of those matrices which are representable as products of unitriangular matrices with entries in that ring is called the elementary group, En. And so we are asking about whether SLN and En is the same. Now we have seen that if we are over a field, they are the same, and yeah, one can prove it's always a normal subgroup. And this quotient group is called the special K1 group. Special means because determinant 1, like special linear group of this ring. And if you look at the size of the matrix, you could say the nth K1 group, right? And of course, this has also generalizations to other groups, like we call them Chevrolet groups, like the symplectic groups, the orthogonal groups. You all know the classification of simple groups, and you can take several semi-simple and so on. Yeah? So I'm talking today about the special linear group. I wanted just to mention that all this theory has also been developed for other groups. So now the first general observation from a point of a topologist or of a complex analyst. So if A, this matrix in SLN, can be written as a product of triangles, then we can put a real parameter in the interval 0, 1, like a homotopy parameter, in front. Here I mean, of course, in front of each entry in this triangle. And you immediately see that t is 1, we start with a of x, and t0, we have the constant identity map, right? This gives a homotopy of our map from x to SLN, which we try to factorize to a constant map. And these maps are called null homotopic, constant, homotopic to the constant map. So if a map factorizes, then it necessarily has to be null homotopic. And it turns out that even in the algebraic case, you can imagine everything are polynomials, the entries here. And then t is another variable, and it's obviously algebraic in this extra variable t. And in that case, one speaks about a one null homotopy. Now the homotopy is not only defined for like the real interval 0, 1, but for the complex numbers. But still at 1 it is your original map, at 0 it is the constant map. So, and here's another way of phrasing it. The null homotopic maps form the path component of identity in SLNR. Yeah? SLNR is a group because SLN is a group, so you can multiply these. And the constant identity map is the identity of this group. And the path component of the identity are those who are homotopic, and these are those which are null homotopic. Okay. Let me talk a little bit about the history. So, trying to show that a lot of famous people worked in this field. The first very general result is, of course, commutative Banach algebras. It could be continuous functions on a compact topological space, right, with subnorm. Or, there are in holomorphic cases like H infinity, bounded holomorphic functions, and so on. There are plenty of examples, and John Milner, in his book on K-theory, already explains that if you have a Banach algebra, the entries are not in whatever ring, but in the Banach algebra, then SLNR and the elementary group is the same. Okay, so this is a very, very general result, but of course it does not apply, for instance, to continuous functions on a non-compact space or to holomorphic functions. Okay, so now let me, even sorry for teaching you a little mathematics in this talk, Euclidean rings. It was very well known that for Euclidean rings you can factorize. I'm trying to explain that in the case of SL2R. So we have a matrix, and the entries here are in a Euclidean ring. And I don't pay much attention what is in the second column, but A and B is my first column. And the ideal generated by the two elements A and B is the entire ring, because A times this minus B times that is 1, so they generate the whole ring, right? The determinant condition tells you they generate this ring. And now if we take, let's F be the Euclidean function, like if you have polynomials in one variable, it's the degree of the polynomial, or in the integers, it's just the integer, right? So the Euclidean function, a Euclidean ring, has a division with remainder, and that's what we do. we divide this A by B, and we get a remainder which has a smaller degree, you could think of, right? A smaller value of the Euclidean function. And now we make an elementary row operation. We multiply from the left with this matrix. It means that we subtract the Q times the second row from the first row. And of course, then we end up to having this remainder here in the first row, right? And then we do the other way around. We divide now the B with remainder by this R1, get a new remainder R2, which has an even smaller Euclidean function. And then we do Q2 times the first row, subtract from the second one, and we end up with this. And you see we go up and down, and after finitely many steps, we end up with first column, where one of the two is the greatest common divisor, because that's the end of the Euclidean algorithm, right? Say alpha is the greatest common divisor, and the ideal was the whole ring, and so the ideal by alpha generates the whole ring, which means that alpha is an invertible element of that ring. And then you do the same as you are used to do over fields. Alpha is like a non-zero number, and you go up and down a little bit more and make it to the 1, 0. This is like we all used to do over fields. And once you have the first row to 1, 0, since we started with a determinant 1 matrix, here is also a 1, right? We have not changed determinant by these elementary row operations. And so that means we have reduced the matrix by elementary row operations to identity, meaning it is a product of unitriangular. So this is a very simple proof for Euclidean rings. And then, this is the first thing which I summarize here. If I take, for instance, polynomials in one variable, which is an Euclidean ring, because it's Euclidean, it factorizes. So the elementary group is the same as SLNR. However, there is no universal bound on the number of factors. It depends on the matrix I'm starting with, how many factors I need. And you can imagine that Euclidean algorithm can go for so and so many steps. You can always make up, say, 2 polynomials that the Euclidean algorithm would need 1,000,000 of steps. And you cannot do better than Euclidean algorithm, which is proven by van der Kallen. So there's no universal bound. Then the first bad news. Cohn found this counterexample. You see immediately it has determinant 1. The entries are polynomials with in two variables, and he can prove that there's no way to reduce the full degree. Degree is 2 of all entries, and there's no way of reducing this degree 2 by any elementary row or column operations in that ring of polynomials of 2 variables. And then the first very famous result comes, that if it's not SL2 but SLN and any number of variables, then it factorizes. And I see here, I'm saying it's a byproduct of his, and his is Suslin, Andrei Suslin, from Leningrad. As a byproduct of his solution to the Serre conjecture was about algebraic vector bundles over Cn, I'm saying in my complex analysis mind, whether they are trivial or not. And he proved that independently with Suslin, and Suslin got Fields medal, and not only for that, but for the K2 group. Okay, so you see there are some remarkable result. And now I'm coming to some very, very new, or rather new result. And it turns out it's only SL2. Has not much to do with algebraic. It's only SL2 is differently than N. And null homotopy has to replace by the A1 null homotopy. So it's exactly the same as in all categories. Here this result is due to Anastasia Stavrova. And of course, in the time of Suslin and all those people developing K-theory, the A1 homotopy was not developed. It is developed by Morel and Vojevodsky, who got the Fields Medal for that. And please allow me to be a little bit proud of my alma mater. Anastasia Stavrova comes from the same university as I was educated at, and she proves that whenever you have a semi-simple Chevalier group, but no SL2 factors, and yeah, whatever a regular C algebra is, but the algebraic functions from a smooth affine algebraic variety are like that. And what you need is what I said, the algebraic null homotopy. So you add one variable. This x was called t before by me, was the parameter for the homotopy. And now it's like an extra variable in the complex numbers, I would think. And yeah, you see at point 1 it's your original map, and 0 it's the identity. And so if this is a one null homotopic, then it's a product of entries in polynomials or polynomial functions on this smooth affine algebraic variety. So yeah, I'm not sure whether she is giving that results, but she is one of the leading experts in K-theory nowadays. And now let's go to topological results. There was a person whose name is Wasserstein, Leonid Wasserstein. Some people may have heard about the Wasserstein distance of measures in optimal transport. That's the same Wasserstein, but it's falsely attributed to him. Anyhow, when Wasserstein was a young student in Moscow, Gelfand was organizing some, he called it research seminar for undergraduates. And these undergraduates were asked to present research questions. And Wasserstein said, why don't we look at this factorization problem with continuous functions, continuous factorization? Yeah, Gelfand said, yeah, okay, if, then do it holomorphically, but it's all not interesting. Anyhow, Wasserstein had a different opinion, and he was going around for many, many years and tried to activate people, and he even activated the Fields medalist Fürsten, and they proved if you take continuous functions on R3, then it factorizes. Yeah? R3 is contractible, right? So null homotopy is given for free, and you can factorize. And then later he proved it, you know, in a very short paper. And here is a little difference to the algebraic case, namely, okay, n is the size of the matrix, and D is a dimension of a normal topological space. And there is a bound on the number of unipotent matrices depending only on the dimension of the topological space and the size of the matrices. And then you can factorize any null homotopic continuous mapping as a product of unitriangular continuous mappings. So, yeah, this number of bounds is theoretical, existing, very few instances that we would really know the best bound. And now I'm coming to the holomorphic case. Yeah? So in the holomorphic case, Michael Gromov asked the factorization problem for this means holomorphic function on Cm. So holomorphic functions in several variables, and yeah, SLN as we usually deal with, and he calls it the Wasserstein problem. So it's in this very interesting paper, published '89. And he says in that paper that even the continuous version is wildly open, although, as you have seen in the slide before, in '88 it was already published by Wasserstein. What is the reason for this? The reason for this is that that paper was a most controversial thing in the several complex variables community. It took him maybe 5 years to publish that paper, and he did not do any revision to it, just sent it to the next journal until this Journal of American Math Society took it. And he didn't even care that in the meanwhile Wasserstein had solved the continuous case. He did no revision of that. But most interesting part of this is a proposal of a new Oka principle. So Oka principle is something very old in several complex variables, and it's a principle roughly saying that if you can solve a problem locally, holomorphically, and there is, in a certain wide sense, a global continuous solution, then you will also find a global holomorphic solution. This is very briefly explained what Oka principle is. And the Oka principle was a big success in the German several complex variables of Hans Grauert and Reinhold Remmert, and many of their students contributed to this, what then got the name of Grauert's Oka principle. And there it was about maps or sections in locally trivial bundles where the fibers were complex Lie groups or even homogeneous spaces of complex Lie groups. And the main thing, which is sort of used as a linearization technique, is the exponential map from a Lie algebra to the Lie group. So the Lie algebra Lie group correspondence was heavily used. Now, Gromov says, oh no, that's not what you need. You need any sort of linearization procedure. He calls it spray, or dominating spray. And when I entered this several complex variables in '91, all those people from the Grauert-Remmert school considered this paper of Gromov just a big crap. Gromov has no clue of several complex variables. The paper did not contain very precise statements, and when he made an attempt of proof, it was obviously wrong. So he claimed things with basics in several complex variables, which everyone knew, and he claimed wrong things about them. Yeah, so what was the point? The point was that the several complex variables community, led by Grauert, Remmert, and those students of them, just said, ignore this. Just ignore this is a big crap, although it was used by Gromov and Eliashberg for a very important theorem that Stein spaces can be embedded into some minimal dimension spaces. And even another student of them used it then to the real optimal dimension. And this school said, no, it's not allowed to use this. It's no proofs, it's not even clean statements. And in '91, I started work with my advisor on the Oka principle, but on a version with group action. Goes totally in a different generalization direction. We had just the case of Grauert and maps into Lie groups. And just with some additional symmetries. This is another issue. And we also thought a little bit, I mean, I was totally unexperienced, a new PhD student, but my advisor said, no, this is impossible. Even without symmetries, it's not clear what to do, just never even look at that. So we looked at it, but we gave up. And then there were people who understood that this paper of Gromov is full of ideas, and one needs to find out what of all he is mumbling there could be put on to solid ground. And there was Josip Klobevnik, and he had just Jasna Bresel as a new PhD student, and they tried to resolve the mystery. What exactly could be proven and stated correctly? And then Franz Fosnowitsch joins them, and he takes the lead. And this is one of very important contributions to the several complex variable theory. Over 2 decades, he and all his collaborators in Ljubljana developed something which now goes under the name of modern Oka theory. So just finding the good formulations, making Gromov's visionary ideas into theorems, and it has been a very great success for our area of mathematics. So modern Oka theory is mainly contained in this wonderful book of Franz Fosnowitsch, and he is invited also at ICM Philadelphia to speak. He was already invited as plenary speaker of the European Congress of Mathematicians. And now we go back to factorization. So this modern Oka theory is really the cornerstone in what we could prove with Björn Ivarsson, just a holomorphic version of this factorization. We have a Stein space, a holomorphic map. It should be null homotopic. And then there is some bound, depending on the dimension of the Stein space, size of the matrix, that we need so many holomorphic mappings into these triangles so that we can factorize all holomorphic matrices, so to say. Yeah, so that was more or less the story. I end up with congratulations to this 50th anniversary of the complex analysis seminar, which I consider to be the most active place in several complex analysis in the whole world. And many thanks from all the several complex variable communities to the founder of this great seminar. Yeah, thank you for your attention.
Thank you very much, Frank, for your wonderful lecture. Let me start for questions. Any questions, remarks?
So Frank, I have a curiosity.
Yeah.
What if you consider, which is a case that I know quite well, infinite matrices, like infinite holomorphic functions, so when you
Yes. There is a part of K-theory. There is something called unstable K-theory and stable K-theory. So this what we are doing when we keep the size of the matrix. It's called the unstable K-theory. And stable K-theory is when you plug in SLN into SLN plus 1 by adding just 0, 0, and a 1. And then you are wondering, if I have this matrix, maybe I cannot factorize it in SLN into elementary, but maybe in SL much more bigger, right? And this is what is called stable K-theory, which is a little bit easier. So there are these results, but I'm not the specialist for this. I just know it's a little bit easier, if I'm not saying something wrong. No, yeah. Yeah.
One question. So in the simplest possible case, for example, to the last theorem with Iverson, you just take X to be complex plane, like C.
Yeah.
Do you have any bounds, upper bound on this?
Yeah. We have some bounds, and I should also make a remark, which I maybe did forget. That this factorization problem has created even some new mathematics, and there's something called the best stable rank of a ring. And it turns out in the complex analysis case, only holomorphic functions on one-dimensional object, like on the complex plane, have this best stable rank 1. And best stable rank 1 is the most general thing. And there you prove that exactly as over fields, always 4 factors. This is some results of who, I don't know. At least the most general result for all Chevrolet groups is due to Vavilov, and it's based on a trick by Oleg Tavkin. Anyhow, so this case, this case is sort of easy. But that is the only case in complex variables that we have best stable rank 1. Yeah.
You have done a lot of, you found a lot of results of this kind also for other groups.
Yes.
Recently you worked on the
Symplectic,
group,
yeah.
right? Symplectic also with Gaofeng?
Yeah, with different, yeah, so if you want, I try to show you what is for the symplectic group here. See, for the symplectic group, I was expecting your question. For the symplectic group, we have these elementary matrices right here. Of course, it's 2n by 2n matrices, and this is an n by n part. Here's identity, and this here is a symmetric matrix, but you can also use those. A is upper triangular, and this means inverse transposed. And you will immediately say, hey, come on. It's upper triangular. This inverse transposed is lower, but this is not a triangular matrix. So this would be the lower, this would be the upper. But it turns out that in K-theory, people use another symplectic form, much more convenient for that. Oops, sorry. Namely, so those matrices I presented, they were symplectic with respect to the standard symplectic form, which we, at least I, knew. And then, as we know that there's only one non-degenerate anti-symmetric bilinear form over a field, and only if the dimension is even, right? And you can use this one. And L1 is the matrix with 1 along the skew diagonal. So it has 1s here, right? Not on diagonal, but on skew diagonal, and here's minus this. And if you use this form, that means that you revert the order of the last basis elements. Here's the ring to the power 2n. Think of C to the power 2n, then those matrices I presented become unitriangular. So, and then we could prove also this elementary factorization. And funnily enough, maybe I have it on the slide, I'm sorry for that. Here's all our results. Yeah, I just want to make a funny thing, that if you look for the number of factors, if you use only those, sorry now for jumping up and down, well, if you use only those here, where here you have a symmetric matrices and you forget about this part. Even over the field, it seems to be over general fields unknown. Here the specialist will tell us, but I have found that over the field of complex numbers, it was proven that 5 factors are enough for those. And this is a group of people from Beijing. One of them is a former PhD student of our friend Zhou from the Academy of Science. So, yeah, this greater variety also, these other matrices make it more easy, and this restricted form is more complicated. And we could relate the number of factors between them and so on. And I haven't found over any field. These guys use, of course, the Jordan normal form, right? So it's over, I would say, probably over algebraically closed fields, it should be okay. But Jordan normal form is what makes things very complicated when you go from linear algebra to parametric linear algebra, because Jordan normal form is not continuous. right? And so, yeah, okay. Thank you.
Can I ask about the holomorphic case?
Yeah, holomorphic case?
Consider 2 by 2 matrices.
Yes.
So has anybody considered 3 by 3 matrices?
Yeah. No, our theorem is okay. Now something happened here. Wait a second. Okay, so I'm not sure what happened. Now I have to go back somehow. Sorry. So our theorem is for any n. Here you see. Here, yeah, this is SLN, right? For any n. And the funny thing is that this is a result from K-theory. If I enlarge the size of the matrix, the number of factors can only drop. So SL2 has the biggest number of factors, and if you enlarge the size of the matrix, and asking about triangles, which are of course now bigger, of course, then it can only drop. This is some general result. I'm not sure to whom it addressed. Could be Wasserstein and Dennis or something like that. Yeah. This is.
I think Arson wanted to ask.
Can you say something about the parametric versions of the problems?
No, parametric, I meant that the matrices depend continuously on a parameter or holomorphically. This is what I call in a very general way parametric, right? It could be in any ring. You could ask about C infinity functions or whatever you want. This is a sort of a parameter in my very general understanding.
You have these types of questions when you keep things fixed. You have a parameter that goes along say, the line segment and you keep the endpoints fixed. You already have holomorphic factorization, continuous inside, and be homotoped to
Not.
fixed endpoint.
No, yeah. You mean some sort of like the homotopy theory in the Oka principle? Not fully. I mean, yes, there is some reason for that we always have to do like the K-theorists and project to, say, the last row or last column and do inductive proofs. And the Oka principle is not applied to the whole factorization problem, but to a more specific way, which comes from first multiplying and then projecting to the last column. And therefore, we did not really look at this. And there's another thing, which I have to say, that there are holomorphic matrices. For instance, this cone example, which I started with, wait. Here, yeah, the example of cone. It's obviously a holomorphic example as well. And holomorphically, you need 5 matrices to factorize that. Continuously, you can do it with 4. So it cannot be sort of the simple-minded Oka homotopy principle. There must be a little more complicated version, but we haven't. Yeah. Thank you for the question.
Questions? I'd just like to mention that lately I started looking at Oka theory in a little wider setting, when you take not just a single Stein manifold as the source, but you take a family of them.
Yeah.
And that could be maybe
generalized to that setting. Yeah.
So far it hasn't been. So far we know that for Riemann surfaces it works fairly well with some continuous or smooth dependence on of structures on the parameter. In higher dimensions there is a substantial complication.
Yeah.
Maybe
I read your paper. Yeah, I know that.
So
Yeah.
there is a complication, but after you put that natural condition, then somehow it works too.
Yeah.
But many of the arguments are much more difficult than in the.
Yeah.
Or, I mean, additional problems appear at every step, so it's
Yeah.
But maybe it's a.
Maybe it's a project for the future. Yeah, yeah. You see, whenever I come to Ljubljana, I get some new ideas.
Okay, so let's thank the speaker again. Now, according to the schedule, we would have a longer break, but actually I propose that we make only a shorter break, and then we'll have a longer break thereafter for the coffee break. So I would propose that we start in 10 minutes, which means 5 minutes after 3. Okay?
We only have this? Okay.
Yeah, so, and I'm not sure how we probably press the escape, right?
Well, anyway, it's Filippo now. I'm the last one, so.
Okay, but I'm still pressing here the escape, and then he should just open his file somewhere. We can maybe close my file here. Wait a second. Just here, I think we can close my file.
It is open twice, your file.
Yeah, yeah. They were already open, so I made some sort of double open. So yeah, this is his file. And now there should be the full screen, right?
This is control.
Yeah.
I don't know how to go to
Yeah,
full
yeah, they
screen,
will help
so.
you.
Okay.
Yeah, yeah, so.
So the next speaker of this afternoon is Professor Filippo Bracci from University of Rome, Tor Vergata. This is Rome 2. Filippo Bracci, I think we first met in towards the end of the 1990s. I was regularly going to Italian conferences, and that's where we met. And then we have been friends ever since, and we visited each other very often. So Filippo is certainly one of the leading mathematicians of the several complex variables in a very general sense of this field worldwide. And he has worked on a remarkable array of different sub-areas of the field, from geometric function theory to holomorphic dynamics to Leibniz equations to prime ends theory, and name it. So it's so I'm really amazed how many things he has touched very successfully. And also he has been, I think, very important in the University of Rome for obtaining grants, money. He had ERC grant in the previous decade. He was very instrumental in getting large grants to the department of Tor Vergata. And now I hear that he's moving to the University of Florence, which is good for Florence. So today Filippo will talk to us about something which I think is probably new to him, another field. And this is holomorphic contact geometry. So the title is Hyperbolic Contact Symplectic Lifts.
So, thank you very much, Franz, and thanks to everyone. I'm really very honored to be here, and it's a great pleasure. I actually think the first time I came to Ljubljana was 2004, maybe, something like that, and since then I visited, and many people from Ljubljana came to Rome, including Josip, Barbara, Franz, and then Luca spent, I think, 1 year, Luca Botzteiler, with me in Rome, and then I also had Riccardo Golini, which now I'm talking joint work with him. He was my master student in Rome, and then he came to Ljubljana for the PhD, and then finally decided to settle here. So, I mean, there was a lot of connection, and I'm always, I agree with Frank that this seminar, this complex seminar, has been probably one of the sources of complex analysis of all Europe and all the world, and especially, I mean, in Europe was probably one of the main ones. So thank you very much. I'm very, very glad to be here. So actually, what I'm going to talk today is about something that, well, in a sense is new for me, but actually it's a joint work with Ben McKay from Cork and Riccardo Golini, who is here in Ljubljana. But with Ben, we started to work on this in 2008. Except that at that time, let me try to explain, and then I will tell you. Oh, is it correct like this? Okay, so let me start with the motivation setup. What are these contact symplectic lifts, the hyperbolic equivalence, and something about automorphism. So about motivation, what I was studying mostly was the opposite of what Franz was studying. That is hyperbolistic. Kobayashi hyperbolic manifold are rather at the opposite side than Oka manifold. And hyperbolicity is a kind of, you all know, Kobayashi hyperbolicity is a distance or a metric on a complex manifold, which, since it is contracted by holomorphic maps, is very useful when you want to study properties of holomorphic maps, or even trying to classify and to understand which manifolds are similar. However, not always, I mean, not all manifolds are hyperbolic. whenever you have a complex line, non-trivial complex line inside your manifold, then it cannot be hyperbolic. So here what I do, I consider a complex contact manifold. I will come later with precise definition. And you can consider holomorphic disks which are tangent to the distribution given by this contact form, so the so-called Legendrian disk. And now, actually, exactly like in Kobayashi's theory, you can define a sub-Finsler. Actually, the proper word would be sub-length function, because it does not satisfy, I mean, the indicatrix is not convex in general, so it's not really a norm. It doesn't satisfy the triangular inequality, but still you have a measure to length vector on the complex tangent bundle. And so what you do, you consider all these disks which are tangent to this distribution, and you define this kind of pseudometric, and then you can define an integrated pseudo distance by taking curves which are we join 2 points and are tangent to this distribution. And well, you say that the manifold is V hyperbolic, I call it this way, if this is really a distance. I mean, it's not just a pseudo distance. So every different point has positive distance. And this, in a sense, generalized Kobayashi hyperbolicity. Actually, here I will focus on contact manifolds, but actually the same definition up to here you can give for any Pfaffian system, or I mean any bracket generating holomorphic distribution on complex manifold. That's exactly the same. And well, Franz and with Ben McKay we arrived up to this point. I mean, to this definition, and then once you assume that your manifold is hyperbolic, you can actually look to the group of automorphisms which preserve the distribution. They become isometry with respect to this metric. And then using this abstract nonsense of linear Lie algebras, you can compute the dimension. And then the natural question is, okay, what are the example where you get the maximum dimension? And that's where we got stuck with Ben for years. But then Franz found this very interesting, very non-trivial example of a contact structure on C3 for which C3 is hyperbolic with respect to this structure. That's kind of amazing. I mean, C3 is what the most non-hyperbolic thing you can figure out. And then Riccardo was trying to understand the group of automorphism of this contact structure. So during one of these meetings that were before in Levico-Terme, in this several complex variable meeting, we started discussing with Riccardo and Ben, and then we decided to work together. And what I'm going to tell today is about this result. So the main question is, can you produce how can you produce V hyperbolic manifold? I mean, manifolds which are hyperbolic with respect to contact structure and which are non-trivial, in the sense that if you take a Kobayashi hyperbolic manifold, you put there any Pfaffian distribution, then it's going to be hyperbolic with respect to that one. But that's, I mean, it's a kind of cheating, okay? So the idea was to try to produce a new example and classify this hyperbolic manifold. And what we use is what we call contact symplectic leaves. So let me give some definition. A contact distribution, always for me, will be holomorphic, on a complex manifold of odd dimension is a co-rank 1, so it's a distribution of dimension 2n on the complex tangent bundle, which is locally given as the kernel of a contact form, that is a holomorphic 1 form which has this property. Okay, so this is a contact distribution. Now, if you keep a holomorphic map from the unit disk into your manifold, you call this a V Legendrian disk or a V disk if it is tangent to the distribution everywhere. And then you can define, since there exists, of course, since you have Darboux coordinate locally, then this exists. And then for every vector which sits in the distribution, you can define a length, which is exactly like like in the Magee. So you keep a phi, which is a holomorphic map from the disk into M, which maps 0, let's say, to P, and whose differential at 0 is lambda times V. And then you take one where lambda is positive. You can always arrange it this way. And then you take the infimum 1 over lambda, exactly like in Kobayashi. Except that now you can give the length only to those vectors which belongs to the distribution, not to all the vectors. Anyhow, Jean-Pierre de Maillet already used this definition, and he proved that this is actually upper semi-continuous. And he used only this metric. I mean, he didn't study the distance when he was studying jet bundles in his argument related to solve the Kobayashi's conjecture. And okay, now if you keep a piecewise smooth curve, which is tangent everywhere to your distribution, you can define a kind of integrated length of this curve simply by integrating the metric along the curve. Okay, so it's that's what you do. And there is this theorem which is called Sussman's orbit theorem, which tells that whenever you have such a bracket generating distribution, so in particular if it is a contact distribution, then every 2 points of M can be joined by piecewise smooth curves tangent to V. And this means that actually you can define a pseudo distance. It might be 0, I mean, but anyhow, you can for any 2 points of the manifold, you keep the curve which join these 2 points and is tangent to V, then there exist such curves. So you take the length of all those curves and you take the infimum. And this gives a pseudo distance in the sense that it satisfies it's non-negative and it satisfies the triangular inequality. But except that it might be 0 when the 2 points are different. Okay, that's why it's a pseudo distance. Actually, this is like, I mean, the Sussman orbit theorem, the way I see is when, the way I believe it's true is because when you go with the windsurf and you want to go from here to there and you have the wind coming in this direction, you cannot go directly this way. So you have to go zigzag, no, to go there. And that's exactly what Sussman orbit theorem tells. Okay, so I give a definition. The manifold is V hyperbolic. V is my contact distribution if this is a true distance. Okay, while I call it complete V hyperbolic if besides being a distance, it is also complete in the sense that this becomes a complete metric space. Now, what are the basic properties? Well, first of all, this is always finite. My manifold is always connected, okay? Otherwise, you work on connected component of the manifold. So it's always finite and it is continuous. If it is V hyperbolic, the manifold, if and only if the distance induces the manifold topology, exactly like in Kobayashi. The proofs are basically literally translation of original proof. And there is a Schwarz type lemma. If you have any Legendrian disk phi, then the disk decreases this V distance with respect to the Poincaré distance of the unit disk. Actually, you might think that in Kobayashi, and actually this was the first definition of Kobayashi, I guess, of Kobayashi distance, he used chains of disks, right, going from one point to another. So you take chains of disks, and then and here you could do the same. I mean, you could consider chains of V Legendrian disk going from one point to another, and then take the infimum. And it's very easy to see that the distance that you defined by, I mean, the inner distance related to this metric, so defined by the infimum of the integrated length, is always less than the other. But we don't know whether the two are equal. I mean, in Kobayashi, they are equal. This is Royden's theorem. And the reason why they are equal in Kobayashi is because the distance is going to be Lipschitz, actually, in every direction. While here, if you think about sub-Riemannian geometry, what you get is the so-called ball box theorem, where you know that in many directions it is actually kind of Lipschitz, but there is one direction, the so-called bad direction, where it is one half Elder continuous. And that's probably, this is what might prevent this to be equal. Anyhow, this I don't know. I don't know of any example where they are different. I don't know how to prove them. And by the way, we don't have a ball box theorem for this infinitesimal v distance. So now contact symplectic lifts. So here was the point. You have this. You assume that they are hyperbolic. Now you look to the group of automorphism of the manifold which preserve the distribution V, and then you can compute, you can estimate from above, you give an upper bound on the dimension of this group, which is going to be a Lie group, a real Lie group. However, even in the case I'm going to tell, the bounds that we get turns out to be never sharp. So it's very hard to find examples. That was the point where also Riccardo came into to play with us. Okay, so here we decided to add some symmetries in our picture. So a Reb vector field is a holomorphic vector field of the manifold, which does not belong to the contact distribution at any point, but whose flows preserve the distribution. So it's an isometry. If you look to the flow, this is going to be an isometry for this kV distance. And well, this is a fact that I mean it's also in real geometry. If you have a Reb vector field, then there exists a unique global contact form, so that the distribution is the kernel of this contact form, and they satisfy this condition. And conversely, if you are given a contact distribution which is the kernel of a globally defined on the manifold contact form, then there exists a unique Reb vector field which satisfies this condition. So assuming that there exists a Reb vector field, then it means that the distribution is given by a global contact form. So for us, a Reb manifold is given by a manifold with a contact distribution and a Reb vector field, which we assume to be C-complete and acts freely on the manifold. So that's what we ask. A Reb manifold, so there is this contact distribution, this Reb vector field, and which acts as a C-complete proper, freely action on M. And we call it a proper Reb manifold if the action is also proper. This is our definition. Okay, then you do have a holomorphic symplectic manifold. I recall the definition. It's an even-dimensional complex manifold endowed with a holomorphic symplectic form. So we say that a contact symplectic lift is the data of a manifold with this contact distribution, and so it's a Reb manifold, and a holomorphic symplectic manifold, this S omega, with a map from M to S, a holomorphic surjection, such that pi is a C principal bundle, and the action is given by the flow of the Reb vector field. So the flow of the Reb vector field at this complex line, which are vertical, let's say in this way, and this zeta is the contact form, so the differential of this is related to the symplectic form by this formula. We say that a contact symplectic lift is C infinity exact or holomorphically exact, depending whether the form omega is C infinity exact or holomorphically exact. The form omega is closer, right? Because it's a symplectic form. So what we prove is the following, which to us was quite surprising because of this C infinity exact, that for every proper Reb manifold, so if you are given this manifold with this contact structure and this Reb vector field, this is going to be the total space of a contact symplectic lift of a C infinity exact holomorphic symplectic manifold. And conversely, whenever you keep a holomorphic symplectic manifold for which its symplectic form is C infinity exact, you can construct a Reb manifold for which this is the C infinity, the C principal bundle over it. Okay, so this and this for us was quite quite strange that you don't need the holomorphically exact, you just need the C infinity exact. That was what was the point. And moreover, if you have two holomorphic manifolds which are the base of the same contact symplectic lift, then they are essentially biholomorphism, and even symplectomorphism in the most rigid sense. The form goes one to another. So if you start from above by a Reb manifold, then downstairs you get essentially unique symplectic holomorphic manifolds. But actually, the converse is funnier, because if you start on the other end by a C infinity exact holomorphic symplectic manifold, then you can find different Reb lift in the sense of this triple, which are in one-to-one correspondence with H1 of S. So it's a topological classification. Although the object is, this M is going to be a C principal bundle over S. So the classification of C principal bundle is given by H1O. So it's, for instance, on Stein manifold, all C principal bundle, rank 1, they are trivial, but here it's not. You just look to this one. And the equivalency here is the most natural one that you can think of. So these are equivalent if there is the two manifold M are biholomorphic. They are equivariant with respect to this Reeb action, and both the contact distribution and the vector fields, they correspond. But still, this is the effect that if you start with the Reb manifold, then downstairs you get only one up to biholomorphism, holomorphic contact holomorphic symplectic manifold. But the other way around, it depends on the topological issue of the manifold S. So as I said, C principal bundle of rank 1 up to equivalence over complex manifold are parameterized by H1 SOS. Okay, the cocycle are just in H1 OS. So in particular, if S is Stein, this is 0, and then every C principal bundle is holomorphically trivial. And then it means that if you start with this S, which is symplectic holomorphic, and Stein, then M is biholomorphic to the trivial product S times C. However, if H1 of S is not 0, then you can give on S times C as many as H1 as C non-equivalent different structure as contact symplectic lift. And actually, this really is like that. For instance, if you consider S to be the disk times the punctured disk, and you take the symplectic form dz wedge dw, this is also holomorphically exact, then all possible Reeb lift upstairs are given by S times C with the kernel of this contact form. And you see that here there is this C, and C belongs on is any complex number. In fact, H1 of this manifold here is just C. So that's why you have as many as C. And they are all different depending on this one. Okay, now I come to the main question. So we wanted to produce example of manifolds which are hyperbolic with respect to contact structure, in the sense I told you before. And what we found is the following. We have a contact symplectic lift. So M is our Reb manifold, the total space of this C principal bundle over S. And then it happens that M cannot be, of course, Kobayashi hyperbolic, right? Because it's a C principal bundle, so there are fibers which are C. However, this is V hyperbolic if and only if the manifold downstairs is Kobayashi hyperbolic. And it is complete V hyperbolic if and only if downstairs S is complete Kobayashi hyperbolic. So we have this equivalence. And so this allows to give plenty of new examples. For instance, take any pseudo-convex bounded domains with H2 DC 0. Then, sorry, here is probably is 1. Okay, then D times C, yeah, here is 1, as V contact structures, which are V hyperbolic, because every bounded every bounded domain in Cn is hyperbolic, right? And here you can put, for instance, on D you can put the dz wedge dw as a holomorphic symplectic form or whatever you want. Well, if you keep any bounded complete hyperbolic domain, then again here is H1, then this product has V contact structure which are complete V hyperbolic. So in this way you can find as many examples as you like, just starting from, I mean, in general every holomorphic symplectic manifold, but here you just take any bounded domain and then you take any holomorphic symplectic form which is C infinity exact. So there you can find plenty. And well, yeah, sorry, no, this is about, yeah, sorry, I take it back. This H2 is correct because it means that any holomorphic symplectic form is C infinity exact. Okay, so this is the issue. But anyhow, you can find in this way many, yeah, that's what I wrote before, after. Implies that every is C infinity exact, so whatever holomorphic symplectic form on D you take, then you can lift to get a V hyperbolic structure. And yeah, complete hyperbolicity implies tautness and pseudo-convexity. That's why you will come with pseudo-convexity here, and here you don't need, but anyhow. Okay, then just a very rough sketch about hyperbolicity. Why this is true? Well, the main issue here is to go from downstairs upstairs, because I mean the map pi from the Rib manifold to the symplectic manifold, it contracts the distance. That's quite easy. So I mean if you have a hyperbolicity or complete hyperbolicity upstairs, it's well, not completely, but almost straightforward to prove that downstairs you have the same. So the problem is to go backward. Well, you do have, oops, what's going on? Okay. You do have this estimate, as I said, and this allows to say that the metric upstairs to the, I mean, you take the projection, and then since you have this kind of Schwarz lemma for a Legendrian disk, then you get this estimate. And then you integrating along curves, you will get that these are, this behaves in this way. So this means that if the base manifold is hyperbolic, then this is positive whenever P and Q belongs to different fibers. That's okay. The problem is when P and Q lie in the same fiber of pi, because I mean here is the same point, so here is 0, so this formula doesn't give you anything. And as I said, usually in this Sub-Riemannian geometry world, in real geometry, what they use is the so-called ball box theorem to prove this type of result. However, well, we are not expert. I'm not an expert in this Sub-Riemannian theory. However, it seems apparently that this ball box theorem requires additional hypotheses on this on this length function that we don't have here, or at least we don't know how to prove. So that was a way we tried at the first, but he couldn't. So what he did was actually to get a localization. In this sense, maybe I will, yeah. We define, we fix a point, and then you can find a Stein open set in S, where you have coordinate Z1, let's say Zn, W1, Wn, so that on this chart, the manifold upstairs is biolomorphic to the product, and the contact form is given something like dy equal to minus z dw. That's essentially, I mean, you have local standard coordinates. Then you define a bounded tube in this way, taking the base point on this chart u, and then y you stay in between these two pieces. Now what it happens is that when you take any Legendrian disk, which is centered, stay in this in a ball of radius r upstairs with respect to this distance v, its image stay in this tube after rescaling, and then what you discover is that the Legendrian disk, which are centered in this ball of this radius, up to rescaling they are contained in this tube-like. But this tube-like is Kobayashi hyperbolic, and then you get this kind of inequality, that the metric is bigger than a certain constant times the metric of the tube, and since it is hyperbolic, then you get this estimate from below. And so this means that actually whenever you go even from one point on the same fiber to the next one, when you move in y direction, then still you gain speed. And so the length of this curve up to a constant is bigger than the Euclidean length in y. And this means that even on the same fiber, this, the distance is positive. Okay, now I turn, how much do we have?
You still got time, don't worry.
Okay, what that mean? How much?
15, 20 minutes.
Okay. Oh, really? So I was too fast. Then I can come back. So what's about automorphism? This, as I said, was our leading question with Ben that we couldn't face, and then Riccardo had a better bound, but still was not a good bound. We don't know actually the good bound. Anyway, so you take this hyperbolic contact symplectic lift, and then you can define this real Lie group out V of M, which means they are all automorphism, so holomorphic diffeomorphism of M, which has the property that they preserve the distribution or the contact form up to a factor. They are the same, and then they form a real Lie group. Now, by an old result of Bochner, I guess, this in this case, since they turns out if this is hyperbolic, then this turns out to be a group of isometry, and so by an old result of Bochner, they form a real Lie group of finite dimension. And then what you do have is that upstairs you have this group. Downstairs, you have the group of all automorphism of S, which have the property that they preserve up to a constant factor the symplectic form. So we call this out C omega S, okay? And then there is a natural morphism of Lie group from this group upstairs and the group downstairs, whose kernel is given by the flow of the Reb vector field, so as dimension 2, real dimension 2. And therefore, you have this formula, which tells that the dimension of the Lie group of automorphism upstairs is less than the one of symplecto, let's say, conformal symplectomorphism downstairs plus 2, okay? And this, of course, is contained in this group, so you have this one. And moreover, if you have this topological condition on S, then this map is going to be also surjective. This means that in general you cannot lift automorphism, conformal symplectomorphism downstairs to automorphism preserving V upstairs. But if you have this condition, then you can glue. You do in a local chart, and then you see that this condition is the right one to glue together. Okay, so we have this formula. Now, there was Isev who spent a lot of years in trying to classify, well, in effect, he succeeded in many cases, the hyperbolic manifolds according to the dimension of the Lie group of its automorphism. And then what we wanted to do was to try to understand, at least in this case where you have this symmetry given by the Reb vector field, whether we can say something about the dimension of this group. So we said, okay, let's start from the lowest possible dimension, which would be S of dimension 2, okay? And then, so M has dimension 3. Because there the top dimension, according to Isev, is given by the ball. But then we got this result, and okay, if you carefully look to this, you will get that actually the maximum possible dimension using Isev result here would be kind of 8, I think. But what we prove is the following. If the manifold upstairs, your Rib manifold, has dimension 3, and it is hyperbolic, then the group of automorphisms preserving the contact distribution have dimension between 2 and 7. All cases are possible, but in the case where the dimension of M, the automorphism group, the V automorphism group of M is 7, then there is essentially only one possibility. M is bilomorphic to the ball times C, and its V structure is given by the unique, up to equivalence as I said before, contact symplectic lift of the ball of dimension 2 with this fancy holomorphic structure, so holomorphic form. So it's dz wedge dw divided by 1 minus z to the power 3. Okay, you would expect that the highest possible dimension would be when you don't have any factor, right? But that's not true, because if you don't have this factor, I mean, if you just take dz wedge dw, then the group of conformal symplectomorphism of the ball preserving these are just a rotation, so it's u2. So you get dimension 6 upstairs, not 7. The reason why this form is okay, because the group of automorphism of the ball, which are preserved up to a constant multiple this form, are all automorphism of the ball which fix the point 1, 0. And this is a group of dimension 5. That's why you get 7 upstairs. And yeah, this is what I was telling. And here I give you some other example. If you take B2 with the standard complex structure dz wedge dw, then the dimension here is 6, because downstairs you have the u2 on the base. So it's not 7. 7 is, I mean, kind of funny. And if you take the bidisk with something similar to this one, then you come up with a group of automorphism fixing the point 1, actually in the 1, 0, and then still you get a dimension 3 group here downstairs, which means a dimension 5 upstairs. And if you take the bidisk with the standard symplectic structure dz wedge dw, then the group of automorphisms is 4, because here downstairs you get what is u1 times u1, right? So it's just rotation in the first variable and rotation in the second, so it's dimension 2, and here you have dimension 4. And here if you add, these are just examples, in the sense that this one is the only example of dimension 7. These are just some examples we found, but here we don't have any classification, okay? We rely on Isev classification for this point here, as I said, because we started to say, okay, if here you have a certain dimension, this tells you that the group of automorphisms downstairs should have this dimension minus 2. And then Isev provides some classification, but then that's not enough, as you can imagine from this example. So, well, and this result, I mean, to prove that that's the only one is quite complicated, at least for me, because it uses a lot of results about solvable subgroup of the B2 and the bidisk, and some differences among them. Okay, so here there is this other example, and then for dimension 2 it means that simply you might take something which has no automorphism downstairs, and then you come up with something which has dimension 2. We do have some bounds for dimension 5 of M, but actually you can get a bound, I mean, in terms of numbers, but this number you get, as I was always joking with Riccardo and Ben, because they I mean, they are expert in Lie algebra and Lie groups, and then from time to time they came up, oh, we have a better bound. They said, okay, just write whatever number you found, because still in this example it's clear that whatever number you can get from this abstract consideration doesn't work. So I mean, so we really don't know, not even in this case. So when Ben and I started, this was exactly try to find example according to this to the topest to the higher possible bound for this number, but we couldn't find any example for this top dimension. In fact, even in this case, it's very special. You get 7, which is not expected by making any abstract kind of results with Lie group and Lie algebra, I guess. Okay, so just a brief summary of my talk. So we have this proper Riemann manifold, which are in one-to-one correspondence somehow with the C infinity exact holomorphic symplectic basis, and you can and then hyperbolicity downstairs goes back to hyperbolicity upstairs. And well, in dimension 3 we have a tight control classification of the automorphism group. Okay, then I think I'm over, and Kavala lepa, and thank you very much for your attention.
Okay, questions?
Answers.
I have a trivial question. The standard example, the standard contact structure on C2 is a lift of the standard symplectic on
You mean
C3? It's a standard. It's a lift of the one on C2, right?
right?
Yeah.
But so you mean so you start from what? From C2 and
C2 with the volume form, DCVW.
Yeah, in this case, yes.
Yes.
Yeah, because that's trivial. So it's C3, and so it's dy. I mean, it's exactly the formula we wrote. I mean, comes what you asked for. The answer comes from. Come from the definition we gave of. No, I think it's below. Okay, from this formula here. If you take the standard formula in C2, then pi is just the projection on the first two variables, let's say, and then you see that the D of the contact structure upstairs is the pullback of the contact form. Right. So this zeta is exactly.
What you call the Lagrangian projection.
Maybe, yeah.
Yeah. There is one thing related to which I couldn't do. Namely, you mentioned at the beginning my theorem on existence of a hyperbolic contact structure on C3. By the way, this was made. I think there are many very different ones, but I didn't discover any way of distinguishing between them. Because the construction is very flexible. The construction is actually strongly using a certain construction by Josip Globevnik of the two Hilbert domains with certain shapes. I mean, in the way how they intersect. Hyperplane, for example. So it's made by pulling back the standard structure from some such Fatou-Hilbert domain, and the domain is made in such a way that you get hyperbolicity. But complete hyperbolicity I could never do. Have you done?
No, actually, I think I asked you once you gave this talk, and I asked about completeness. Here I think that even completeness was quite hard in the sense that you don't have a standard procedure. So what we could do is using localization. So that might be a possibility. One should try to localize this in terms of something that you know that it's going to be complete. But the structure of your example are, Riccardo tried to compute the automorphism group, and probably it's going to be discrete in your case. So it's, this is a different part from this. But
actually, I would think that these examples are almost generic. That's my feeling. I mean, I didn't prove any of that, but it's my feeling that, that the generic contact structure on C3 is sufficiently twisted. Actually, my real interest in this was whether there could be an analog between the theory of real context structures, when there is this dichotomy between the so-called tight structures and the over-twisted structures. The center one is tight, and then the over-twisted. This was Eliasberg's classification of context structures on R3, real, up to isotopies. And I was trying to think what could be an analog in the holomorphic world. I couldn't come up with any. Then I realized that I couldn't come up with in any simple way by an example of a context structure for which I would be able to show that it's not the standard. Either I couldn't show anything or else it was the standard. And so in desperation I said, well, let's try something very different. And this was very different from.
Yeah.
So this is very wide open field, I think.
Yeah, I think so.
Good. So in case there are no questions, then let's thank Filippo again.
Thank you very much.
And now we have coffee break. I propose that we meet again at 4:30, so 4:30. So the coffee break is, there is some coffee and water in the corridor just opposite. I wish to ask you not to bring any drinks, liquids in this hall. Thank you so much. Wait a second. Ah, that's great. So the last talk of this afternoon will be given by Professor Antonio Alarcón from the University of Granada. Antonio has been our friend since about 15 years ago, and this started in a very unusual way. One day I got a very pleasant invitation from two people from the University of Granada that I didn't know, none of them, and they said, why don't you visit us and we can talk about possible collaboration because we think that the methods that you are developing could be useful. And so I visited, and then Antonio came the next year for a month here as a postdoc at the time. And this then really developed wonderfully in our collaboration, but also with other members of the group, in particular with Josip and Barbara. And I'm really very happy about this because this is a good example of how different fields, which are close but not the same, should really talk to each other more. I also wish to say that Antonio is now leading the group of, the research program in this field in topology and geometry at the University of Granada. And he's very visible, especially in the field of minimal surfaces, but he also learned a lot of complex analysis by this exchange, and vice versa. We learned about minimal surfaces. And Antonio was an invited speaker last year at the Spanish National Congress of Mathematics. Not only invited speaker, but a plenary speaker. And in fact, he talked about the same subject that he's going to talk about today to us. Please.
Okay, thank you, Franz, for the invitation. When I visited Ljubljana, when I first visited Ljubljana in 2012, I never imagined I would have the honor of participating in an event like this. So I'm truly honored. So hvala lepa, moji prijatelji. And okay, today I'm going to talk about the jump problem. This is not a terribly new stuff, but I have chosen it for two main reasons. One of them will become very clear during the lecture, and the other one is that actually the seminar for complex analysis has witnessed and contributed to the development of this problem for over a decade. So I think the subject is very suitable for this for today. Okay? So this story began in 1977 when Paul Young posed the question whether there are complete, immersed, or embedded complex submanifolds in a complex Euclidean space with bounded image, so with the range contained in a void. Completeness is a very natural condition to impose on a Riemannian manifold when one is interested in its global properties. So recall that an immersive manifold is complete if pulling back the Euclidean metric into the submanifold via the immersion induce a complete metric space, so Cauchy sequences converge or geodesics go on indefinitely. And this, by the Hofrinow theorem, is equivalent to the immersion sending divergent path in the submanifold into path in Euclidean space with infinite Euclidean length. So the first answer to this question came very quickly, and it was resolved by Peter Jones, who gave examples of complete bounded holomorphic immersions of the unit disk into C2, embeddings into C3, and proper embeddings into the ball of C4. His method of proof is very analytic. He used this method called the big mean oscillation technique. And then we had to wait for over 3 decades in order to to find more examples, more general examples. And this was in a series of papers with Lopez in Granada and with France. And in general, we gave examples of complete proper holomorphic curves in the ball of C2 and embeddings in the ball of C3 for very general families of minimal surfaces, for instance, having arbitrary topology, possibly infinite, or normalized by a border Riemann surface. Our construction method is much more geometric. In particular, we use the approximate solutions to the Riemann-Hilbert boundary value problem. We also use approximation theorem for theory for holomorphic functions on open Riemann surfaces, Rungian, Mergelian, and so on. And a little bit later, Barbara showed that the unit ball in CK admits a complete proper holomorphic embedding into the ball of Cn whenever the codimension is high enough. And for this, she used peak functions, right? Okay, so all this construction, as I have just said, in this construction, they are used very different tools. But actually, the underlying idea for the proof is the same in all cases. So let's think first in the real case. So the real case is much simpler. So let's imagine that this is a surface in R3, and let's imagine that it is complete. So the length of divergent path is actually infinite. And we want to deform this surface, the real surface in R3, to insert it, to put it inside the ball in a small region of a sphere. How can we do that? In this way. In this way. This is easy. And this works perfectly in the real case, because this deformation, besides very strong, preserves the intrinsic length of divergent path. So the lines, the divergent paths that were drawn in the piece of paper, they still have the same length. And so this is a solution in the real case, very easy. In the complex case, it's much more difficult because such a strong deformation completely destroys the complex structure in the submanifold. And so the submanifold is not holomorphic anymore. So what we do in the complex case is different. The general idea is to start with a compact complex submanifold with boundary, and in a recursive way deform the submanifold near the boundary in order to make the boundary distance from a given interior point larger and larger, while keeping the submanifold suitably bounded. Okay, so more precisely, imagine that, or assume that in the step J of our induction, we have, for instance, a complex curve in C2, compact with boundary, and the boundary line in the boundary of a ball centered at the origin. Then what we do is to push each boundary point of our complex curve an amount of 1 over j in a direction orthogonal to the position vector of that particular boundary point. So in this way, we increase the intrinsic diameter, the boundary distance from a fixed interior point, by an amount of 1 over j. But by Pythagoras' theorem, the resulting curve is contained in a bigger ball, and the radius of this new ball are related in this way. We pass from this radius to this one. So in this process, we have increased the boundary distance by an amount of 1 over j, while the extrinsic diameter is increased in the order of 1 over j squared. Okay? Then if we do this in a recursive process, since the series 1 over j diverges in the limit, we obtain a complete complex curve. And since this sequence converges, the limit complex curve will be contained in a limit ball, and so it is bounded. So this is a very general idea, then using different tools and different approach lead to the different results that I just mentioned. Okay, so next question is that the Young problem is much more difficult when we consider embedded submanifolds of low codimension. The reason for this, and in particular the most difficult case is the problem for embedded hypersurfaces. Okay. The reason for this is that complex submanifolds of dimension k in Cn are generically embedded whenever n is at least 2k plus 1. This means that if we have in this dimension and codimension, if we have a complex submanifold, we can apply a small deformation to it in order to make it embedded, to remove all self-intersections. Okay? However, when the codimension is smaller, then you apply small deformations and the self-intersection never disappears. This is the same situation that happens in the real case. For instance, if we have a real curve in R2 in the plane and it has a transverse self-intersection, then if we apply a small deformation, the self-intersection will be always there. However, as soon as we allow to deform we add one more dimension, then we easily, with a small transformation, we get rid of the self-intersection. And the same happens in the complex situation and in arbitrary dimension. Okay, so at that time, the problem for existence of complete embedded complex hypersurfaces in the ball remained open. Yeah, for instance, in all these results that I mentioned in the previous slides, whenever that we have an embedding, for instance here, the codimension is so high that the embeddedness is generic. For instance, here we have curves in C3 or in C4, here again curves in C3, and in the result by Barbara, the codimension is so high that the embeddedness is generic. So the problem remained open. Okay, so the first solution to the embedded jump problem for hypersurfaces came in the lowest dimensional case of curves in C2. And this was a theorem with Lopez saying that the ball, the unit ball in C2, admits a complete properly embedded complex curve. So a positive answer to this, the embedded jump problem in the lowest dimensional case. The proof still uses this Pythagorean idea of deforming in orthogonal direction near the boundary, orthogonal direction to the position vector, in order to increase the intrinsic diameter while keeping the extrinsic one suitably bounded. But it is much more elaborated, much more difficult. So in this case, the idea is the following. Oh, sorry. Now, in the inductive step, say in the step n of the recursive construction, we assume that we have a complex curve embedded, compact, with boundary, and with the boundary line in the boundary of a certain ball. And then we pass to the ball of radius bigger by this number, right? Then, in the first step of the proof, we construct what we call a tangent net. This is a finite, this is the union of finite elementary slabs in R4, in C2. A slab is just a region of space between two parallel affine hyperplanes. And we have finitely many of them. And we construct the net in order to satisfy two properties. The first one is that the net contains the boundary of our complex curve. And the second one is that if we have any path inside the net and connecting the boundary of the smallest sphere with the boundary of the biggest sphere, so any path like this or like that, then the length of such a path is comparable to 1 over n. It's comparable to 1 over n. Okay, this is the first step of the proof, the construction of the net. Then in the second step, we deform our initial curve in order to push its boundary to the boundary of the bigger ball. And we do it in such a way that the new part of the curve is contained inside the net, inside the union of the slabs. Okay, in this process, this process creates self-intersections, of course. And we cannot get rid of them by small deformations. But what we can do is to apply a surgery which replaces every normal crossing, every normal self-intersection in our complex curve by a small annulus, okay? And so we do that, and we get rid of self-intersection, and we obtain an embedded complex curve with a boundary in the boundary of the bigger ball. The problem is that applying this surgery creates shortcuts. It decreases the intrinsic boundary distance. But since the new part of the surface of the curve is contained in the net, the boundary distance has been increased in an amount comparable to 1 over n. And again, Pythagoras is in our team, and in the recursive process we do the task. Okay. So the method of proof in this theory is relies very strongly in the fact that we have curves in C2. It's very strongly of analysis, complex analysis in one variable. And in particular, it does not worry, it cannot be extended to higher dimensions. And so it remained open, the question whether the same result holds true in higher dimension, whether the ball of Cn for n greater or equal than 3 admits a complete properly embedded complex hypersurface. Okay, so it was, I think it was 2013 when I came to Ljubljana, and I went to the seminar for complex analysis, and I explained this theorem and its proof in details. And among the audience, there was this great man here, Josip Globernich, who I'm very honored and proud to call my friend. And he thought that he could do it better. And he was right. And then he proved this theorem. He proved an extension of our result to arbitrary dimensions. So he proved that that the unit ball in Cn admits complete closed complex hypersurfaces. Okay, this is a beautiful theory, and it was published in the Annals and well deserving, in my opinion. And the beauty and the importance of this theorem is, in my opinion, not so the statement itself, but the method of proof, because his method of proof was completely groundbreaking, was completely different to any previous construction related to the jump problem, and has strongly influenced every subsequent development. So I think that honestly, I can say that the day before Josip posted his paper in the archive, I think honestly I can say I was the main expert worldwide in the jump problem. But then at the following day I saw the light. So his example, he instead of, as previous examples, he instead of looking for an inversion or an embedding to construct the example, he found examples implicitly as level sets of highly oscillating holomorphic functions on the ball. And so recall that if we have a complex manifold X and we have an unconstant holomorphic function, then its level sets are closed complex hypersurfaces in the manifold, possibly with singularities. And so the family of level sets gives a holomorphic foliation of the manifold by closed complex hypersurfaces. However, when we take a level set of a regular value, which are most of them by Sart's theorem, then the level set is smooth and hence a properly embedded complex hypersurface. Okay, so with this in mind, his method of proof is the following. It consists of two main steps. The first one consists of constructing rather involved labyrinths of compact sets in the ball. So each piece of the labyrinth is a compact convex set in the ball, and the labyrinth consists of infinitely many pieces. Of course, in the picture there are only finitely many, but it consists of infinitely many pieces which accumulate in the boundary of the ball. And this labyrinth has two main properties. The first one is that the labyrinth is so tricky, so involved, that whenever that we have a path, a divergent path in the ball, so a path going to the boundary of the ball, and being disjoint from the labyrinth, or even intersecting only finitely many pieces of the labyrinth, then the length of such a path is infinite. But on the other hand, the labyrinth is so simple or so nice that it is possible to construct a holomorphic function on the ball such that the function is in norm greater or equal than 1 or bigger than 1 in the first piece of the labyrinth, than 2 in the second one, than 3 on the third one, and so on. Then it turns out that if we take a level set of this function f, and we take a level set, it will be a closed complex hypersurface in the ball. So if we take a divergent path on the level set, this path is also divergent in the ball. But since we have a level set, the level set itself intersects and moves finitely many pieces of the labyrinth. And so the divergent path does so. And so it has infinite length. So, oops, sorry. So every level set of this function is complete. Right? So what he actually proved is that in the unit ball there is an unconstant holomorphic function, all of whose level sets are complete. And so in particular, the ball admits a holomorphic foliation by complete closed complex hypersurfaces. Then, by Sart's theorem, most level sets of the function are smooth and is properly embedded. And this is why the second theorem implies the first theorem. Okay? So in the rest of the time of this lecture, I'll try to explain the proof of this theorem here. But I'm not going to explain the original proof by Josip, but I'm going to explain a simplification which uses, in the second step of the proof, which uses holomorphic approximation theory. So in particular, once we have the labyrinth, in order to construct the function f, I will use the Oka-Weil theorem. So this theorem says that we have a state manifold and a holomorphically convex compact set in our manifold. Then every holomorphic function on a neighborhood of the compact set can be approximated uniformly on the compact set by entire functions, so by holomorphic function defined on the whole state surface. Well, of course, recall that the ball is a state manifold, so the theorem will apply in our situation. Okay, so this will be in the second step of the proof. But in order to achieve to the second step, we need first to deal with the first step of the proof, of course. And so if we want to use this theorem to construct a function, then the labyrinth will have to have some good convexity properties. So let me spend a couple of minutes to talk about holomorphic convexity and the construction of the labyrinth. Okay, so just as a motivation, recall that a compact set in a real Euclidean space is convex, is geometrically convex, if whenever we choose a point out of the compact set, there is a fine hyperplane which separates the point from the compact set. This is geometrically convex. But this is the same thing as that there is an affine function in Euclidean space having a level set, so an affine hyperplane separating the point from the compact set. So passing this notion to the holomorphic category, we say that a compact set in a state manifold is holomorphically convex if and only if there is a holomorphic function on the state manifold having such that there is a level set of its norm separating a point outside the compact set from the compact set. Okay, so this is holomorphically convex. In the case when the state manifold is a Euclidean space, then the function f can always be chosen to be a polynomial, a holomorphic polynomial. And this is why holomorphically convex compact sets in Euclidean space are called polynomially convex. And this is what we need today to construct our labyrinth. Okay, so what do we need about polynomial convexity? Well, in case n equal to 1, it is very easy to identify when a compact set is polynomially convex. The only condition is that the complement is connected, so the set has no holes. This is easy. In higher dimension, it's much more difficult. But we know that compact geometrically convex sets in Euclidean space are polynomially convex. This is important today. And moreover, our labyrinth will consist of union of different pieces. So it is important for us to understand when a union of compact sets is polynomially convex. And in this case, we have this result. We know that the union of two disjoint compact convex sets, geometrically convex, I mean, in Euclidean space, the union of two is polynomially convex. However, the union of three is not polynomially convex in general, but the union of two is fine. Also, we know that the union of three mutually disjoint closed balls in Cn is again polynomially convex, but in general, the union of four is not, okay? And also, we have this fundamental result in polynomial convexity, which is known as the Kallin's lemma. It says that if we have two compact convex sets, so geometrically convex, and inside one of them we have a polynomially convex set, then the union of this polynomially convex set and the other compact convex set is again polynomially convex. Okay? Good. Okay, then with this in mind, let me explain how is the labyrinth that we are going to construct. So we shall construct a type of labyrinth that we call tangent labyrinth. And this is a labyrinth which is contained in a spherical shell. So we have a spherical shell in Cn of radius r and capital R. And inside the spherical shell, we have a labyrinth consisting of finitely many pieces. And the labyrinth is something like that in the picture. It consists of different levels. In my picture, it has 3 levels: the blue one, the red one, and the green one. And if we pay attention to one of the levels, then what we see is that it consists of finitely many pieces, and they all are supported in a sphere centered at the origin. And so each piece of the blue level, for instance, is a ball, is a round ball, a closed round ball in the affine real tangent space to the sphere. And in addition, the center of the ball is precisely in the sphere, okay? And we have finitely many of them. And all pieces of the same level have the same radius. And the radius is so small that the pieces of one level do not hit the sphere supporting the pieces of the next level. So something like that in the picture, okay? Good. Then these tangent labyrinths have two very nice properties for us. The first one is that if we have a tangent labyrinth in a spherical shell, then if we consider the union of the small ball, the small closed ball, and the tangent labyrinth, then this set is polynomially convex. Okay, so the union of the small ball and the tangent labyrinth is polynomially convex. Why is this? Okay, so consider the small ball. This is the ball of radius r, little r, and the first piece of the labyrinth. So this is a union of two disjoint compact convex sets. So this union is polynomially convex. Then we add the second piece of the labyrinth. And then by the geometry of the tangent labyrinth, we can find a compact convex set, this red one, which contains the ball and the first piece, and it is joined from the second piece. By Kallin's lemma, the union of these two pieces and the third one is again polynomially convex. And we continue with the next piece of the labyrinth, of the tangent labyrinth. And we are in the same situation, since by the geometry of the tangent labyrinth, there is a compact convex set, which is disjoint from the first piece, and which contains this set here, which we already know that is polynomially convex. So by calling lemma, the union is polynomially convex. And we continue this way, and infinitely many steps, we show that the union of the ball and the whole tangent labyrinth is polynomially convex. Okay, and this is the first property. And the first nice property that tangent labyrinths enjoy is that whenever that we have a spherical shell, we can construct inside the spherical shell a tangent labyrinth with the property that the length of every path crossing the spherical shell and being disjoint from the labyrinth is as large as we wish, say bigger than any given constant delta. Okay. The proof of this lemma is in fact rather involved. You have to work a good while, but it is totally elementary. It only uses basic trigonometry. The idea is that we have to put many levels, and we have to choose carefully the center of each piece of the labyrinth. The idea is to make sure that when we have a path crossing the spherical shell and being disjoint from the labyrinth, then when the path escapes from one level of the labyrinth, it meets in front of it a piece of the next level. And so in order to avoid it, it must go in a direction orthogonal to the position vector. And then again, when it escapes from the second level, it meets in front of it a piece of the next level. And to avoid it, it has to go in a direction orthogonal to the position vector. If we have so many levels, then we force the curve to move most of the time in directions orthogonal to the position vector. And so Pythagoras is again our friend, and everything goes fine. Okay? Good. So now with this, with the labyrinth in hand, and having in mind the Oka-Weil theorem, let me explain the proof, or outline the proof. So we have to show that the unit ball in Cn admits a non-constant holomorphic function, all of whose level sets are complete. So the proof is the following. To begin, we take a sequence, an increasing sequence of positive numbers converging to 1, like this. And then for each j, we consider the spherical shell of radius rj and capital Rj, and inside of it, we take a tangent labyrinth, Lj. And we choose the tangent labyrinth such that the length of every path crossing the labyrinth, crossing the shell, and being disjoint from the labyrinth is at least 1, or bigger than 1. Then we call L to the union of all these tangent labyrinths. So now each Lj consists of finitely many pieces, but L is an infinite labyrinth which accumulates in the boundary of the ball. And by this condition here, it has the property that if we have a divergent path on the ball, hitting at most finitely many tangent labyrinths, then it has infinite length. Okay? This is the first step of the proof, the construction of the labyrinth. Now the second step. The idea is to, in an inductive process, we construct a holomorphic function f, which is a limit of holomorphic functions in the ball, and we make sure that f is in norm bigger than j on the labyrinth Lj for each j. So as I explained earlier, every level set of such a function intersect at most finitely many pieces of the labyrinth, and so it is complete. Okay, so for the induction, what we need to construct is a sequence of holomorphic functions on the ball such that the function fj is close to fj minus 1 in this ball here, or radius rj, and such that fj is bigger than j in the labyrinth Lj. It is clear by these two conditions that in the limit we obtain a holomorphic function in the ball, which, if all the approximations are close enough, the function f still satisfies this estimation here, and so all its level sets are complete. Okay, so for the basis of the induction, we begin with any holomorphic function in the ball, and for the inductive step, we assume that we have the function fj minus 1, satisfying these two conditions, and we proceed in this simple way. Okay, we now consider the union of this ball here, where we want to approximate, and the tangent labyrinth in the spherical shell, where we wish to obtain this condition here. Okay, this union is polynomially convex, and it is a disjoint union. So we can define a function little f in this union by making it equal to fj minus 1, which is the function in the previous step, here in the ball, and to be any constant bigger than j, for instance, j plus 1, everywhere in the tangent labyrinth. So since this union is disjoint, the function f is well defined and is holomorphic. And since the union is polynomially convex, the Oka-Weil theorem applies and gives us a holomorphic function on the ball satisfying these two conditions here. And this is the proof. Okay. Okay, so after Joseph theorem, it was not clear whether his examples give a rare type or a very particular type of solution to the embedded jump problem for hypersurfaces, because his examples enjoy a priori very particular property, because his examples, he gave examples of complete, properly embedded complex hypersurfaces in the ball, but his examples are a lift in a holomorphic foliation of the ball by example of the same kind. So in principle, this is a very strong condition. Okay, so it was not clear whether this is indeed a very strong condition or whether it is not. Okay, so on the one hand, at that time or a little bit later, they appear several other constructions of complete complex properly embedded hypersurfaces in balls. For instance, with Joseph and with Lopez, we gave examples with restricted topology and even with arbitrary topology in the lowest dimensional case of curves in the ball of C2. And also there are examples of properly embedded submanifold of higher codimension. And none of this construction is implicit. So in principle, this example here need not take part of a holomorphic foliation of the ball by example of the same kind. On the other hand, there is a very classical result by Serre saying that every divisor in a state manifold is a principal divisor. So in particular, every closed complex hypersurface in the ball, even possibly with singularities, is a level set of a holomorphic function of the ball. And hence, the hypersurface is a leaf in a holomorphic foliation of the ball by closed complex hypersurfaces. So one may be inclined to think that if the given hypersurface V is complete, perhaps one can find a defining function whose level sets are also complete. And it turns out that this second possibility this is what happens. This is what happens. And so we have this theorem, a bit more recent, showing that, in fact, every solution to the embedded jump problem for hypersurfaces is a Globevnik solution. Actually, the theorem says a bit more. The theorem says that every closed complex hypersurface in the ball of Cn, possibly with singularities, and possibly incomplete, is a level set of a holomorphic function on the ball, is a level set of a holomorphic function on the ball, such that all other level sets are complete. All other level sets are complete. So we don't need the given hypersurface to be complete in order to find a defining function for it whose level sets are all complete, except perhaps the given one. Okay? Of course, in particular, if the given hypersurface is complete, then it is a level set of a so-called Globecnik function, a holomorphic function on the ball, all of whose level sets are complete. And so the hypersurface is a leaf in a holomorphic foliation by complete closed complex hypersurface. Okay. Okay. Here is a brief, very briefly, outline of the proof. Okay, the proof broadly follows the proof by Josip, but it presents some important differences and novelties. So we start in the same way. We consider a sequence, increasing sequence of real numbers converging to 1. And we shall inductively construct a holomorphic function and an infinite labyrinth of compact sets. So differently to the proof of Josip, now the labyrinth will be constructed as part of the inductive process. We cannot fix the labyrinth a priori. Okay, so then our labyrinth will be of the same time. Will be our labyrinth L is an infinite labyrinth, and it will consist of a union of tangent labyrinths, each one in each spherical shell. So we have something like here in the picture. We have the ball, we have the given hypersurface, and we shall construct in each spherical shell a tangent labyrinth. And at this very preliminary step, we note that the hypersurface, that in each tangent labyrinth, for instance in this one, there are two different types of pieces of the labyrinth. Those which intersect the given hypersurface, like this one or that one, and those which do not, like this one here. Okay. Okay. So in the induction, we will make sure that the limit function is has the given hypersurface as 0 level set, and we will also ensure that every proper path, the labyrinth will satisfy the state condition, that every divergent path of the ball or in the ball hitting at most finitely many pieces of the labyrinth has infinite length. This is the same thing, and we shall also ensure this condition, which is different than the one in Josip's theorem. We will ensure that for the level sets of the except the 1 over 0, the level sets of the limit function, the limit holomorphic function f, intersect at most finitely many components of the labyrinth for every level set, except perhaps the 0 one. And to ensure this, what we do is to split the labyrinth. When we construct the tangent labyrinth Lj, we distinguish between the pieces intersecting the given hypersurface V and those which do not intersect. So if we look at this piece, since V, which is the blue hypersurface, must be the 0 level set of the holomorphic function solving the theorem, so the pieces intersecting the given hypersurface, we cannot ensure, as in Josip's proof, that the function f is big there. So what we do is to ensure that at those pieces, the function f is small, is in norm close to 0, while on the other pieces we make it big. Then, when we take a level set of such a function, and then since this sequence goes to 0 and this one goes to infinity, it turns out that every level set, except perhaps the 1 over 0, intersect at most finitely many pieces of the labyrinth, and so it is complete. Okay. Okay, in the proof, we use not Occavile theorem is not enough, and so we also need interpolation, and this is given by Cartan-Occavile. So the theorem says that we have a state, as above, we have a state manifold and a holomorphically convex compact set, and in addition, we have a closed complex submanifold B. And now we have a holomorphic function on a neighborhood of the union of the holomorphically convex set and the given closed complex hypersurface. Then this function can be approximated uniformly on K by entire function, approximating interpolating everywhere on V. And this is the main tool that we use. Okay, this theorem admits several extensions. For instance, we can choose the defining function, the little f, solving the theorem. We can choose it when the given hypersurface is smooth, we can choose the defining function to be non-critical. And hence, all of these level sets are properly embedded, are smooth. And so this gives non-singular foliations of the ball. Also, everything holds true for submanifolds of arbitrary codimension. We need not work only with hypersurface. If we have a complex submanifold of some codimension, we can find a holomorphic foliation of the ball by submanifold of the same codimension, and all other leaps being complete. And going further, everything holds true with the ball replaced by an arbitrary state manifold, ended with a Riemannian metric. So we have a state manifold with a Riemannian metric on it, and we can find a foliation by hypersurfaces, all of which are complete with respect to the given Riemannian metric. Okay, so, and the key tool to prove all this, to obtain all these extensions is the result in the ACTA paper by France, which is a Cartano-Cabal type theorem, but for holomorphic submersions, or for holomorphic function with non-critical points. Okay, so to mention some more recent results in this direction and some more general result, we have this theorem with France from last year, that if we have a state manifold with a density property, and we provided it with a Riemannian metric G, and then if we take a proper holomorphic foliation of the state manifold, we can find an automorphism of the manifold which takes this foliation into a complete foliation, a foliation all of whose leaps are complete with respect to that metric. So we start with any foliation, and using automorphism, we twist it a lot near infinity in order to make all the leaps complete. So such things can be done. Okay, so even so, at that time, it was not clear how abundant Globevnik's examples are. Okay, so a Globevnik function, to me, a Globevnik function is a holomorphic function on the ball, all of whose level sets are complete. And it has been very difficult to find a single example of, or to prove the existence of a single example of such a function. And of course, it is not possible to give an explicit example. So one can wonder whether the set of all such functions is small or if it is big. In order to answer that question, I need to recall a bit of Baire category theory. So recall that a set in an arbitrary topological space is called residual if the set contains a countable intersection of dense open sets. Then a topological space is called Baire, is a Baire space if and only if every residual set in the space is dense. So if and only if a Baire space is a topological space such that every countable intersection of dense open sets is again dense. So residual sets in a Baire space are considerably large, are very large, because they are strong, they are dense in a very strong sense. They are not only dense, but if you take a countable collection of residual sets and you intersect them, what you obtain is again dense. So yeah, it's a strong density. And so they are very large. Then we say that the property of elements in a Baire space is generic, or we say that the generic elements satisfy the property if the property is satisfied for all the elements in a certain residual set. And in this sense, we say that almost all elements satisfy the property. Okay, so for instance, in the space of real numbers with the usual topology, being irrational is a generic property. Almost every real number is irrational. If we choose a real number randomly, it will be irrational with a probability of 1. Okay? Then the space of holomorphic functions on the ball end up with the compact open topology, which in this case coincides with the topology of uniform convergence on compact sets, is completely metrizable. This is an easy exercise. And so by the Baire category theory, it is a Baire space. So we are entitled to wonder whether the space, the set of Globevnick functions is big or small in this space. And it turns out that it is big, Globevnick functions are generic. So Globevnick examples are so natural that on the one hand, we have already seen that every example, every solution to the jump problem is like his solution. And also, Globevnick functions are so natural that if we say, roughly, if we choose a holomorphic function on the ball randomly, then it will be a Globevnick function with a probability of 1. Okay? So the theorem said that exactly that, a generic function on the ball, a generic holomorphic function in the ball, satisfies that all its level sets are complete. That is, it is a Globevnick function. Okay, the proof, this is, by the way, this is a theorem of Charpentier and Kosinski. The proof broadly follows the same construction as in Josip's paper. So we again construct a labyrinth as we have as in his proof. So the infinite labyrinth L is the union of the infinitely many tangent labyrinths. Each one is in a spherical shell, and these LJs have the property that path crossing the labyrinth, but being disjoint from the path crossing the shell, but being disjoint from the labyrinth are longer than 1, say. Then we consider for each pair of indices, I and j, we consider this set here, u, I, j, which consists of those holomorphic functions on the ball which are in norm bigger than I everywhere on the tangent labyrinth Lj. Okay, since we have the compact open topology and the tangent labyrinth is a compact set, it is a finite union of compact set, then this set is open. And then so is the union of J of all these sets here. And then we get to this set UI. So UI is the set of holomorphic functions of the ball for which there is a tangent labyrinth Lj, one of the tangent labyrinth Lj, the function f is bigger than y in one of the tangent labyrinth Lj. So this is the union. Then, by Oka-Using-Oka-Weil theorem, as in the proof of Josip's theorem, we can easily see that the set UI is also dense in the set of all holomorphic functions. And so we have a countable collection of open dense sets here in our topological, in our bare space. So the intersection is a residual set, so a very big set. So a function f is in this intersection if for every I there is a j such that the function f is in norm bigger than I in the labyrinth Lj. And then it is immediate to see that every function in this set satisfies that all its level sets are complete in the same way that in the proof by Josip. And so every function in U is Globevnick. And since U is a residual set, so is the set of Globevnick functions. And okay, that's all that I wanted to say. Thank you very much.
Thank you very much for this inspiring lecture.
Okay.
Please, questions? Yes.
I don't have a question. I'll just make one remark on the following sort, that the fact that you called France, invited him to Granada, and then France invited you to come to Ljubljana, and me hearing you explain this in Granada made me solve Young's problem.
Yeah.
Without that, I would have never solved it. So I'm very happy.
Okay, thank you. I'm very happy too. Believe me.
Other remarks or questions? No? Oh yes,
There's something I don't understand, of course, is when you define this UI and so on to say that it is dense, but this means that bounded holomorphic function on the ball, they are just
bounded holomorphic function on the ball. Yeah, this is nothing. If you choose a holomorphic function on the ball, it will be bounded with a probability of 0. It's like choosing a rational number randomly.
One can prove that there are no logarithmic function, bounded logarithmic function, or
I don't know. This is a difficult question. I don't know.
This infers the existence of unbounded logarithmic functions. They are
Yeah.
generic,
Yeah.
but still one doesn't know if they are bounded.
Yeah. This is a difficult question. Yeah.
This is not clear, because it's just by method of proof that you want functions to grow on the regular.
Yeah.
Otherwise, you well imagine that they could be so twisted nevertheless that it's the same property. So it's a good question, yes.
Yeah. It's a good, difficult question.
It's a branching out problem. Okay, well, I forgot to mention that actually our friend Antonio has a birthday today. So let's congratulate him and thank him again.
Well, in the occasion of my birthday, you are cordially invited to a banquet for dinner. Okay.
Right. Now, so, let me say something now. This, if you look at the program, this seems like the end of the official part of the program. But there is a small addition, surprise. Another good friend of ours, and this is Edgar Lee Stout from Seattle, has something to say. Stout was, of course, long-term collaborator of Josip and my advisor. So please, project. It will be a recording. Yeah.
Josip and I met many years ago when he came to Seattle as a visiting professor in the mathematics department at the University of Washington. I met him at the Seattle airport and took him directly to the apartment that we had rented for him. I came the next morning expecting to help him get organized in his new situation. To my surprise, I discovered that he had already rented a car. He plainly had no need of my help in getting organized in Seattle. I am under the impression that Josip came to Seattle to talk to me about Banach algebras and related matters, but by then my interest had moved on to several complex variables. It was not long before we were talking about problems in that subject. We made some progress and were able to publish a couple of papers that were written during Josip's visit to Seattle. Without going into detail, let me give a rough description of some of this work. Some of it is motivated by the result in classical function theory that there are functions holomorphic on the unit disk or on any other domain for that matter, that can be continued analytically into no larger domain. One of the results that Josip and I obtained implies a result on the unit ball in Cn in the same general non-continuation direction. There are functions holomorphic on the ball in Cn with the property that for any complex line that meets the ball, the intersection is a disk, the restriction of that function to the disk continues into no larger domain in the complex line. This settles a problem that was proposed by Nessim Sibani. our results are actually more general than what I've stated, more general as pertains to the domain and also as pertains to the function that we construct. The function that we get is actually in the Neven-Linna class. A paper from a few years later is rather geometric in flavor, and is motivated by another result in classical function theory, namely that a conformal map from the unit disk onto a domain in the plane that is bounded by a simple closed curve. The conformal map extends to give a homeomorphism of the closed disk onto the closure of the domain, the image domain. We also investigated maps from the open unit disk into CN. Among other things, we found that with some hypotheses, if F is holomorphic from the open disk into the plane, into CN rather, that is injective and that extends continuously to the boundary, then F is injective on the boundary. Our work includes results in several other directions. One of our last papers is geometric in flavor. Let gamma be a rectifiable simple closed curve in CN. Let F be a bounded proper holomorphic map from the unit disk into the complement of gamma. Then the derivative F primed of F is lies in the vector valued Hardy space H1, and F extends to carry the boundary of the disk onto gamma as a covering map of the same multiplicity as that of F. There were several other papers that dealt with various topics. The most recent one, which was published in the year 2000, can it really be so long ago, has to do with an analog of Morera's theorem in the setting of boundary values of functions holomorphic on the ball or on other domains. Thus, my period of collaboration, active collaboration with Josip lasted over at least 20 years. For me, it was always a pleasure to work with Josip. The fact of the matter is that Josip by himself was able to obtain generalizations of many of our results, our joint results. Shortly after Josip returned to Ljubljana from Seattle the first time, he did me a marvelous favor. He sent his student Franz Forstnerich to Seattle to study with me. Franz was the kind of student one wants. You point him in a good direction, and then you try to keep up with him. Franz was very well prepared when he arrived in Seattle. The first thing I gave him to read was Henri Cartan's exposition, Mexico City exposition of Grauert's Oka principle. He was prepared to do this. Very few entering graduate students are so well prepared. And as you know, the Oka principle has been a central theme in much of Franz's work for many years. After Josip's first visit to Seattle, he came several more times, sometimes as visiting professor, once as to participate in a conference. We have met at several other conferences: Marseille, Stockholm, Madison, St. Petersburg, Santa Cruz. I don't know where all at this point, and we were always very happy to meet. I have a very pleasant memory that after the Santa Cruz conference concluded, Josip and my wife and I made a very pleasant road trip from up the California coast to finally arrive in Seattle. I have had the pleasure of visiting Ljubljana several times, and indeed have spoken in this seminar. On one occasion, my wife joined me, and on such a visit, and she has still a very warm memory of Josip's gracious hospitality. Josip, you have recently celebrated an important birthday. I'm sure that everyone in this seminar joins me in wishing you many more.
Thank you very much, Lee. Are you with us on Zoom? This is now the question. Can we have Zoom? In principle, this event is also available on Zoom, and so Lee promised that he might log in. It's a bit early for him, but this is Erland Wald. Hello, Erland. Let's see, do we have... Five participants. Can we see the participants? They're there. Yes, okay. So unfortunately, it seems... So it seems that Lee is not with us today, but we have a pleasure of meeting Andrei, Erland Wald that we see here, and Shang Hong Gong, my colleague from Madison. Actually, I have to say that Erland was also invited to come on this occasion, but for health issues, he could not. So it's nice to see you, Erland. Okay, let us now conclude the event. Actually, even this is not a conclusion of the event. I'd like to invite my colleague Barbara Drnovec here to this place.
So I will be very brief. First, I would like to thank the Slovenian Academy of Sciences and Arts for hosting this event. I would like to thank all the speakers for their excellent lectures, and especially to Lee Stout for his valuable contribution. I would also like to thank Josip for establishing the seminar, for giving us the opportunity to celebrate this 50th anniversary, for setting high academic standards, and for providing this inspiring environment for many researchers in several complex variables and related fields. So, as many of you know, I was Josip's PhD student. He taught me to be careful about the details, but to keep in the sight of the bigger picture. He still, when we meet, he still asks me about my research. So being, let's say, curious, but very generous as a mentor. So, dear Pico, I would like to congratulate you on your 80th birthday. I wish you all the best. And I hope that we meet at or after seminar in the future. And with this, I thank you all for coming here today.